Alright, what's up virtual learners? I am going to be showing you two different strategies for how we can subtract across zeros using numbers up to the millions. So this is a 4th grade standard in Virginia, the state that I work. The two strategies I'm going to be modeling for you today are adding up with an open number line and creating an equivalent problem using constant difference. So let's get started. Here is a sample problem. I have 6 million minus 465,074. Now when students try to set this up using the traditional algorithm and they try to do all of this regrouping, they often get it wrong because it's very hard to regroup when you don't have any groups that you can shift except for in that millions place. So when we call this subtracting across zeros, when we have all these zeros here, there's often other strategies that are more efficient than doing traditional subtraction with regrouping, and I'm going to show you two of them today. So the first strategy that I'm going to show you is how you can add up for this. So I'm going to take you back a little bit to smaller numbers so that we can make sense of this and understand why it works. So let's go back to what we know about addition and subtraction, okay? So what do we know about addition? We know that when we have addition, we know one part and another part, and what we do not know is how much is in the whole set. So addition is part plus part would give me the whole, and the whole is what is unknown. Okay, now subtraction is related to addition. They are both additive operations. They are related. So when you have subtraction, you know the whole and you know one of the parts, but you do not know the other part. So when you are subtracting, you're starting with the whole and you're subtracting a part, and what you do not know is the other part. So let's think about this, because addition's pretty easy. Part plus part, you add them together to get the whole. But when you're subtracting, you can take away the part from the whole, but you can also think about this part plus some other part would get me up to the whole. So let's just put some numbers in here just so we can remember what we're talking about here. Let's say that my whole was 5. And I knew one part was 3, and I was trying to think of the other part. For something like this, I could say, another way I could model this would be like, say I have a set of 5 things, and 3 of them are black, and I want to know what part is white. So I can think about that as 5 minus the 3 that are colored would leave me 2 white. But I could also think about that as 3 plus what other part would get me up to 5. And so then I can add on to the 3, and I can think 3, 4, 5. And how much did I add on? 2. So knowing how addition and subtraction are related and understanding that part-whole relationship starts in kindergarten. And if I have a very good understanding of that, then when I start getting harder subtraction problems like 11 minus 9 is a harder subtraction problem because I don't have 11 fingers, so it's harder to take 9 away. But if I was trying to think about 11 minus 9 and I knew how addition and subtraction were related and I understood the part-whole relationship with addition and subtraction, then I could think 11 is my whole, the part that I know is 9, and so then I can think 9 plus what other part would get me up to 11. And so then that's 9, 10, 11, 2 more. And so then I could use this to help me with this. 9, 10, 11. If 9 plus 2 is 11, 11 minus 9 must be 2. So when we talk about related facts, we start talking about related facts. We're not just talking about writing related facts. We're talking about actually using related operations, and usually it's using addition for subtraction. So let's think about how adding to subtract something like this would look with much larger numbers, okay? So, okay, I might set me up double boards here, okay? All right, so now if I'm going back to that original problem, 6 million. And I'm trying to take away or subtract 465,074 to figure out what that other part would be. If I set that up in a part whole box, my 6 million would be the whole. And then 465,074 would be the part that I know. So if I wanted to use addition to think about a problem like this, I would think 465,074 plus what other part gets me up to my whole of 6 million. Now, the way that I can think about this and keep track and organize my thinking would be using an open number line. Now we're flat, right? All right, so I'm going to start with the part that I know, and I'm going to draw a line. I'm going all the way up to my whole, which is 6 million. That's my whole. This was my part that I know. Okay, so now when I'm making these jumps up to my whole, I'm going to be using what I know about place value to help make smart jumps, because if I use place value to help me figure out where I'm going, then when I go to look at the other part that I have jumped up in chunks on my open number line, it will be easier to put those chunks back together. So first things first, if I'm at 465,074, I want to be thinking about what would be the next 10. Since I'm at 74 here, I have 7 tens. So the next 10 would be 465,080, because 80 is the next 10 after 70. So I'm just going to be thinking about where I'm going to go when I'm hopping. For right now, I'm not going to be thinking about how much I have to get there yet. So now this right here is my next 10. After I get to my next 10, the next place I'm going to try to get to is the next 100. So right now, in this number, I have no hundreds. The next 100 would be 100 more. So it would be 465,100. That would be the next number that I'm trying to get to. So now this is the next 100. Once I've got to the next 100, I want to keep going up to the next place value. So if I'm going to the left after the hundreds, I want to get to the next 1,000. So if I'm at 465,000, the next 1,000 would be 466,000. And then that right there is my next 1,000. Okay, now after I get to my next 1,000, the next place value up would be the 10,000. So my next 10,000, I have 6 10,000s, so another 10,000 would get me to 470,000. That is my next 10,000. All right. Now that I'm to my next 10,000, I want to get to the next 100,000. Since I'm at 400,000, the next 100,000 after that would be 500,000, and that is my next 100,000. After I get to the next 100,000, the next place value up would be the millions. So then I would want to get to the next million, which I don't have any millions here. So my next million would be 1 million. And that's my next million. From that next million, I would want to get to my whole, which is 6 million, okay? So now that I have thought about what would be my next 10, my next 100, my next 1,000, my next 10,000, my next 100,000, and my next million, let me look and think about what kind of jumps I would have to take to get from one to the other. So if I'm at 465,074 and I want to get to 465,080, I really need to know 74 plus how much more gets me to 80. And since 4 plus 6 gets me 10, 74 plus 6 will get me to 80. So 465,074 plus 6 would get me to 465,080. Now that I'm there, I need to get from 80 to 100 because both of them have 465,000. So I'm thinking 80 plus how much more gets me to 100. So 80 plus 10 will get me to 90 plus another 10 gets me to 100. That would be 2 10s or 20 that I would have to add. So now that I got to my next 100, 465,100, I need to get up to 6,000. I know that 5,100 plus 9 more hundreds would get me to 6,000 because I know I need 10 hundreds to get to 1,000, but I already have one. So I only need 900. Those 900s would get me up to 466,000. Okay, so now that I'm there, I'm thinking 66,000 up to 70,000. I can also just think 66 plus how much more gets me to 70, and that would be 4, but since it would be 4,000 that I would need. 4 plus 4,000. Okay. So now that I'm at 470,000 and I want to get to 500,000, I'm thinking 70,000 plus how much more gets me to my next 100,000. So I can think 70,000 plus what is 100,000? 7 plus 3 is 10. So 70,000 plus 30,000 would get me to 100,000. So 470,000 plus 30,000 will get me to 5,000. Okay, so now that I'm at, 500,000. So now that I'm at 500,000, I need to get to 1,000,000. Well, 500 plus 500 will get me to 1,000,000. So I need another 500,000. Sorry about that glare. And then to go from 1,000,000 to 6,000,000, I would just need 5 million. Just need 5 million. Like, that's a lot, right? So now if you look at my whole open number line here and you look at how much I jumped up, you can actually see I have 5,534,926. So I already know that the difference here is going to be 5 million from there, right? And then this is all my thousands period. So that's 534,000. And this is all my ones period, 926. So that means that if I have 600,000 minus 6 million minus 465,074, the difference is, or the other part is going to be 5,534,926. And since that is the part that I added up, that is also going to be my difference. This here would be my difference here. So that is one way to subtract across zeros. I'm going to show you another. All right, for this next problem, I'm going to actually keep the same problem of 6 million minus 465,074. But for this one, I'm going to be using the second strategy where I create an equivalent problem using this idea of a constant difference. So let me back up a little bit so we can talk about this constant difference so we all understand why this strategy makes sense to use, okay? So let's go back. We were talking about if we had a problem like 11 minus 9. We said that we could use an addition problem to help us think about this. We said we could think 9 plus what other part would get me up to 11. and we know that that would be 2, right? So what we also know is that if I put 9 and 11 on a number line, let's see, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll just put them here. Okay, so that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and on and on and on. Okay, so if I was comparing 9 and 11 on a number line, and I'm looking for the distance between 9 and 11, the difference between those two numbers, can you see that it's a jump of 2? I can even go like this, 1, 2. So the difference or the distance between 9 and 11 is 2. So that means that the difference between 11 and 9 is 2. So 11 minus 9 is 2. Now remember when I was saying kids are first learning about numbers and they're doing a lot of work on their fingers? Once they get up to facts past 10, they do not have enough fingers. They don't have 11 fingers, so they have to start developing some more efficient strategies. So let's set this number line up again, and I'll show you what I'm talking about when I say create an equivalent problem using constant difference, okay? So now, if I'm trying to do something like 11 minus 9, I don't have enough fingers. I don't have 11 fingers. I can change these numbers both in the same way, and my difference will be the same. So let's say I'm trying to make this an easier problem. I'm thinking, oh, if I only had, if it was just 10 and not 11 because I have 10 fingers. Well, how do I make 11 10? Well, I would just have to take off 1, right? But if I take off 1 from both of these numbers, then I'm turning it into an equivalent problem of 10 minus 8. Well, check this out. What is 11 minus 9? We already know it's 2, right? Well, what is 10 minus 8? Guess what? It's also 2. Let's take a look on the number line and see why this happens. We're going to look at the distance between 8 and 10, okay? So now when I go back to my number line and I'm looking at the distance or the difference between 8 and 10, I can see that there is a distance or a difference of 2. So if I change these numbers in the same way, the distance or the space between the two numbers in my equivalent number sentence will be the same difference or distance apart. That's why I call this using a constant difference. I'm creating that equivalent problem because the difference is going to be the same. So I can use this strategy even with larger numbers. Let's show how you can use it. It's going to make this a lot easier. So say I'm taking this big problem like 6 million minus 465,074. Well, who wants to deal with all those zeros? Nobody does. But guess what? If I took 1 away from that number and I took 1 away from that number, I can create an equivalent problem that would have the same space between those two numbers. So that would give me 5,999,999, because that's 6 million minus 1. And then I could take away 465,073, because that's 1 less. So I took 1 off of both of those to make an equivalent problem. 5,999,999 minus 465,073. These two numbers are both 1 less than the two original numbers that I had, but since I changed them both in the same way, the distance or the difference between my new two numbers should be the same. So these problems should be equivalent. So now if I'm subtracting 465,073 from 5,999,999, there is absolutely no regrouping that I would need to do there. Woohoo! So that's going to be, watch how easy this is. 6 and 3 is 9, 7, 8, 9, 2, 9. 5 and 4 is 9. 6 and 3 is 9. That's not cute. 4 and 5 is 9. See how I'm using that addition even just to do these little facts that I'm doing within the problem? That would be 5,534,926. And just to show how that would look on the open number line, my original problem was the 6 million. And I wanted to know the difference between 465,074 and 6 million. But when I created that equivalent problem by taking 1 away from each of those numbers, I really took 1 away from 465,074 to get 465,073, and 1 away from 6 million to get 5,999,999. But this distance is going to be the same regardless, because I'm just shifting that problem the same amount up or down the number line. So I could have added the same number to both of those problems, but for this problem it made sense for me to just take 1 away from both of them, because then I've created an equivalent problem that does not require any regrouping. So that makes it an easier equivalent problem with a constant difference. So those were 2 strategies that I showed you guys, adding up using an open number line and what I know about place value, as well as creating an equivalent problem using constant difference. Both of them did use an open number line. Both of them required an understanding of a part-whole relationship with addition and subtraction with smaller numbers. So students will have a harder time with this if they do not understand that part-whole relationship with smaller numbers. But usually if you go back and you teach it to them with the smaller numbers, they can then connect it up to the larger numbers with some practice. So good luck, boys and girls.